Alright, so let's go ahead and solve this problem. Consider 1 kilogram of water. It's initially saturated liquid and it is heated at constant pressure until it is saturated vapor. Determine the volume change during the process if the pressure is, and for case A, 20 kilopascal, for B, 1 atmosphere, 1000 kilopascal, and then 5 megapascal. To help organize the information, construct a table down here. This is a suggestion. And so in that table, I'm going to put the pressure, and I'm going to put it all in the similar units of kilopascal. So common unit of pressure, kilopascal. And then I'm going to leave a space here, and then we're going to go to the tables, and we're going to get V sub F. So what is V sub F? That is our saturated liquid's specific volume. And it's going to be a function of the pressure or the temperature, depending on what table you use. At table A2 is a function of temperature, or table A3 is a function of pressure. This has units of meter cubed per kilogram. And then what we're going to do is leave a little space and come over here and put V sub G, and also in units of meter cubed per kilogram. And then we're going to basically use the relationship that if we're interested in the volume and we know the specific volume, we just multiply by the mass. So we'll basically calculate the volume at state 1, and it's in units of meter cubed. And then likewise, we'll calculate the volume at the final state 2 in meter cubed. And then over here what we'll have is we'll have the difference in the volume, V final minus V initial, and that units of meter cubed as well. So that's the goal here. I'm going to try and reduce my font size to make it look a little better. And it doesn't really look that much better, but there you go. Okay, so we'll go to the table. First, we'll go and look for 20 kilopascal. So to do that, so we go to the back of the textbook and we look at our tables A1, A2, A3, etc. And these are for the SI units. So the other would be the United States customary system of units with BTUs, foot and pounds and all that. And we notice that table A2, A3 has the word water and water and water and compressed liquid water and water. So 1, 2, 3, 4, 5 tables of properties associated with water from A2 all the way to A6. Now the first A2 is if you have temperature coming in and you have a two-phase liquid vapor mixture of water. At table A3, if you know the pressure and you're looking for information about two-phase liquid water vapor mixture of the water. So we're going to be jumping back and forth between table A2 and A3. What we're going to do is scroll down. This is table A2. The primary input is this first column, temperature. That's why they put temperature table for the two-phase saturated liquid vapor on water. And then we'll come down and we'll start table A3. And table A3 is pressure is a primary input. And so that first column is pressure in bar. And so 0.04, etc. So we look down here and we're looking for 20 kilopascal, which is 0.2 bar. And right up here is a very important reminder. So 1 bar is 100 kilopascal. So let's do this. 20 kilopascal is 0.2 bar. So we're able to do that conversion. And because it's problematic for a lot of students, they give this helpful conversion factor for pressure going from megapascal to bar and kilopascal to bar. Okay, so we look over here and there's our saturated liquids specific volume in units of meter cubed per kilogram. So it's 1.0172. And no matter how many times I teach this course, some students will forget to look up here, right here. And that's a critical piece of information. And that's saying that they take the specific volume of saturated liquid, V sub F, they multiply it by 1,000, and then stick that result into the table. So if you want V sub F, you take the value out of the table, and you divide by this 1,000, and so you're going to move the decimal point over 1, 2, 3. So 1.0, let's do this copy. I'm going to go back to our table here. So this was, some students would just put that in, but it's not that value. It's 0.0010172, and that is our correct value for V sub F. Let's jump back and take a look at V sub G. It's 7.649. So I'm going to go back here and put it in V sub G. 7.649. Okay, so we have those two values. If you have only 1 kilogram of water, then it's pretty trivial. You just mass of 1 kilogram times the specific volume. It's like you just get rid of the kilogram. 0.00100172 is the specific volume, saturated liquid. Let me go ahead and reduce the font size here again. So do font, and we'll do 10, and hopefully that looks a little better. And then likewise here, 7.649. So when you do the difference, you'll find that the volume change was 7.6479828, etc. You could put more digits, but I think you get the picture there. All right, so if that's the volume change here, so determine the volume change during the process if the pressure is held constant. So our answer for part 1 would be V2 minus V1 equal to 7.64798. If we round that off, you could round it off to just 7.65 meter cubed, box it, and that would be the answer for part A. All right, let's take a look at B. They give us information, but it's in 1 atm for the pressure. So we want to convert 1 atm into kilopascal. So we can go to conversion factors, and in pressure we have 1 atm is this many bar, 1.01325. And what do we know about this 1 atm? Well, it's the atmospheric pressure, and it's special. That's the boiling point of water is 100 degrees C. So we can take a look at the table, and we can come down here and we could say, well, that's almost 1 atmosphere pressure. That's 1 bar. The saturation temperature right up here is almost 100 degrees C, but it's not precisely. So maybe instead of using table A3, we'll jump back and take a look at table A2. And when you look at table A2, let me just help you here. That's temperature again, the first column, pressure and bar. So we'll scroll down. We know the boiling point of water at 1 atm is 100 degrees C, so there's 100 degrees C. And so it says the saturation pressure in bar is 1.014 bar. Students sometimes will be a little perplexed. How come it's not 1.01325? Because if I look over here, that's not 1.014. If I even rounded it off to 4 significant digits, this would be 1.013, not 1.014. Anyway, it's close enough. And because if you only wanted it to 4 digits, and if you really wanted to be closer to 100 degrees C, it really is 1.014 instead of 1.013 is better. All right, so a little subtle thing there. Hopefully it doesn't trip you up. But I would come in here and put in the pressure of 1.014 atmospheric pressure, you can see why I left this column here. It's the saturation temperature in degrees C, and for this it's boiling point 100 degrees C. We can go back to the table and pick off V sub F. V sub F is 0.0010435, a lot of digits, and then V sub G is 1.60818. All right, so those two numbers are repeated when you go for V1 and V2, and the change in the volume 1.607. Close enough, 4 significant digits on that. So if you wanted to come up here and write the answer for V2 minus V1 equal to 1.607 meter cubed, and box it, and that'd be the answer for part B. Let's continue. We want to calculate the value of the volume change for 1,000 kilopascal. So put 1,000 right there. And then it's kind of like I should have emphasized what, a little note, what table did we use? We used table A3 for this one. We jumped to table A2 for that one, and we're back to table A3 again when you are interested in 1,000 kilopascal. So let's go ahead and take a look at table A3. So this is still table A2. Oh, they even notice that. Look at, they're emphasizing, oops, hard to see it right there. This is V sub F is equal to the table value divided by 1,000. Again, they're emphasizing, don't make an error there. That a lot of people, again, forget that header, and that has that value of 10 to the 3 in the header. Okay, so we're going to go to 1,000 kilopascal, which is it's a 10 bar. This is my saturation temperature, 179.9 degrees C. That's my V sub F divided by 1,000, and then V sub G right here. So we'll go ahead and put those into a table. If you want, you can put 179.9 for the temperature, 0.0011273, and then V sub G was 0.1944, and then the volume change comes in at 0.19327, blah blah blah. So we could come up here and write the answer for volume change. V2 minus V1 is equal to 0.19, and if I want it, I'll put 33 meter cubed, and that's our answer for part C. Okay, let's go and take a look at the last one. It's 5 megapascal. Well, what's 5 megapascal? It's 5,000 kilopascal, or 50 bar. And so we'll go to our table. We were down here at 10 bar. We need to jump to 50 bar. And there's the saturation temperature of 264 degrees C, and our V sub F and V sub G values. So let's go ahead and put those in our table. So this was 264 degrees C, 0.001289, and then for V sub G, 0.03944, and then the volume change comes in at 0.03815. Close enough. So we could come up here and we write our last answer for the answer is V2 minus V1 equal to 0.03815 meter cubed. Box it, and that's the answer for part D. Now I left an extra column out here, and what I did was I wanted to calculate the percent increase. And so if you take the volume change, V2 minus V1, and you divide it by V1, it really tells you how much it's expanded from the initial volume. And so for this problem, if you just do that ratio, it's 7,519. So it went up by 7,519. That's how much the volume changed. How about for the second one at 100 kilopascal roughly, or 100 degrees C, 1,540. And the next one, 171 and 30. So these are huge volume changes. Even 30 is still large, but these are tremendously large volume changes at low pressure. This one was table A3 again. Now we're going to go ahead and continue the discussion here, but I'm going to talk about how to plot this. And they don't ask us to do that, but if you look at the data, we're ready to go ahead and plot something. And so let's say I wanted to create a plot, which is a pressure volume plot. Specific volume or volume, either one. Let's do specific volume in meter cubed per kilogram. And this pressure, we'll put it still in kilopascal. Well, the first thing you have to do is figure out where's our maximum pressure, and then divide the y-axis. Let's say this is going to start at 0, go 1, 2, 3, 4, 5,000. So there's 5,000. Here's 1,000. And so it's like I got the value for 5,000, 1,000. This was not. That wasn't the pressure in ATM. I need to fix that. If you wanted it in kilopascal, it's 101.4 kilopascal, or 1.014 bar. Okay, so then the next one down here is around 100. It's going to be harder to see. That's around 100. And then the bottom one is 20. It's even smaller. It's down there, so you have to point in there, just really small. Okay, so we have our idea with the pressure on the y-axis. Take a look at our volumes. Let's take a look at V sub 1, or V sub F, and then V sub G. We'll plot both of those. Well, this is 0.001, blah, blah, blah. The largest value is like 7. So maybe what I want to do is I want to come out here and go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like 10. And then we'd say, well, the largest was 7.6. So that'd be like right in this vicinity, 7.6. And then the next one, 1.6. This is 2, 1.6, 1.6. And then 0.19, you're going to get a lot of information crammed in down in here. And so if we wanted to, all these values are about 0.001, 0.001, 0.001. And so here's like 0.001. It'll be here, 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 and even up here, very close to that y-axis. If we drew a line connecting those, it'd be nearly vertical. And that would be our sequence of states known as saturated liquid states. All right. And then over here we had a saturated vapor, the largest at the lowest pressure, then the next one, and it's really hard to see this, but it'll be, and then it goes, and those are saturated vapor states. Well, we always sketch these on a PV diagram. We never talk about the scale, etc. We just sort of throw it out there. So a lot of times you'll see somebody, okay, and I'll do it all the time. Here's a PV diagram. I'll put it a little steep, come up to the point, and then kick it out like that. All right. But to get this to look like this at all, I would need to plot the the x-axis in a log scale. So just think about that if you plot it on a linear scale with no transformation of the axes, then it would be incredibly awkward looking. But to get it to look something like this in shape, we'd probably put it on a linear on the p, or even log p. You could do that too, but definitely log on the x-axis for specific volume.